Hello folks, in this video we are going to learn about the basics of trigonometry. At the very basic level, trigonometry is the study of the ratio of side lengths in right angled triangles, also known as right triangles. So here's a right angled triangle ABC with a right angle at B. The side that's opposite to the right angle, in this case AC, is called the hypotenuse of the triangle. Hypotenuse, that's a T. Keep in mind that the three angles in any triangle have to add up to 180 degrees, which means that if you take out this 90 degrees, then these two angles A and C have to add up to 90 degrees. A very useful piece of information we are going to exploit a little later. Now for the time being, let's name this angle C as theta. You know, theta is a Greek alphabet. We often use this Greek alphabet to denote angles. The side that's exactly opposite to theta, AB in this case, is called the opposite, OPP in short. And the one that's next to theta, we have three legs of the triangle. One is the opposite, one is the hypotenuse. This one is called the adjacent. Now the opposite and adjacent are not fixed. The hypotenuse in the triangle is fixed. What I mean by that is, if you look at angle A, then the side that's opposite to angle A is actually BC. So this becomes the opposite and this becomes the adjacent. So it really boils down to which angle we are looking at. In this case, we are looking at this angle. Therefore, this becomes the opposite. This becomes the adjacent. Now let's define a function called sine theta, the sine of this angle C, and that is defined as the length of the opposite, OPP, that's the length of the opposite, over the length of the hypotenuse. I'm going to write HYP in short. So for this triangle, sine theta is going to be the length of AB over the length of AC. Define another function and let's call it cosine theta. Now I'm using the term function. Function means something that depends on theta. So we say this is a function of theta, because as theta keeps changing, these ratios will keep changing. So cosine theta is defined as the adjacent over the hypotenuse. In this case, for theta, the adjacent is BC over AC. And one more, I promise this is the last one for the time being though. Tan theta is defined as the ratio of the opposite to the adjacent. So this is opposite over adjacent. In this case, for theta, this is AB over BC. Now cos is actually the short form of cosine, and tan is the short form of tangent. In fact, SIN is also a short form. The actual name is SINE, sine. So the ones in blue are the actual names. Like I was saying a while ago, angle A and angle C have to add up to 90 degrees. So if theta is expressed in degrees, remember you have a choice to express theta in radians. Now assuming theta is in degrees, the measure of angle A has to be 90 degrees minus theta. Now let's write down the three trigonometric functions sine, cosine and tangent of angle A, that is 90 minus theta. Sine A or sine 90 minus theta is equal to the opposite of A. Now the opposite of A is no longer this one, it's actually this one. So the opposite of A is actually the adjacent of C, and the opposite of C becomes the adjacent of A. You see the point? And therefore sine 90 minus theta is actually equal to cosine theta, BC over AC. Similarly, cosine 90 minus theta is equal to sine theta. Let's see how to apply this knowledge in an actual problem. So we have a right triangle over here, and the lengths of the three sides are given. The hypotenuse is 13 units and the two other sides are 5 and 12. let's say this angle is our theta. So sine theta is the opposite over the hypotenuse. So that's 5 over 13. Cosine theta is the adjacent over the hypotenuse. That's 12 over 13. And tan theta or tangent theta is the opposite over the adjacent. That's 5 over 12. Is there a way we could find out the value of theta? How many degrees is this? Yes, we can by the use of something called the trigonometric tables that's got the sine, cosine and tangent of all angles. Let's say we want to use sine. So we know that sine theta is equal to 5 over 13. We change this to a decimal and we get 0.38. And you look up your tables to find out which is that angle whose sine is 0.38, and you will find out that theta is equal to 22.33 degrees. And here's another way to look at this. No matter how big or how small the actual triangle is, as long as the angles in the triangle are the same, as long as you're having a 22.33 degrees over here, the ratio of the side lengths, the actual lengths may be larger or smaller, but the ratio will always be the same. Over to the next topic, the Pythagoras theorem, which is named after the mathematician who formulated this theorem. So we have a right angle triangle over here, and the lengths of the three sides are denoted by the letters A, B and C, where C is the length of the hypotenuse. Now the theorem tells us that if you take the length of any of the sides that is not the hypotenuse and square it, that means multiply that number, the length is a number, right? Multiply it with itself. So if you do A square and you do the same with the other side that's not the hypotenuse, so you do B square, A and B are the two lengths, and if you add them up, that must give you the square of the length of the hypotenuse in the triangle. If it's a right angle triangle, this relationship has to work. Take a note, you cannot just about pick any numbers of your choice and go on to say that they represent the lengths of the three legs in a right angle triangle. They have to be constrained by this relationship. So if someone tells you that there's a right angle triangle with side lengths 2, 3 and 4, the unit doesn't matter, it could be centimeters or meters or whatever. Now 2 square is 4 and 3 square is 9, and 4 plus 9 is 13, but 4 square is 16. Therefore this relationship doesn't hold, which means this is impossible. You cannot have a right angle triangle with these side lengths. However, we could have a triangle, a right angle triangle, with side lengths 3, 4 and 5. Remember, the hypotenuse always has to be the longest side in the triangle. Now 3 square is 9, 4 square is 16, and 9 plus 16 is 25, which is the same as 5 square. So this works. And we could also have a triangle, let's say 6 on one side, 8 on another side, and the hypotenuse is 10. Because 6 square is 36, 8 square is 64, 36 plus 64 is 100, and that's the same as 10 square. So these are also the possible side lengths of a right angle triangle. Remember, the largest number always has to be the hypotenuse. Let's look at a problem then. So here's a right angle triangle where the hypotenuse is 20 units long. One of the other two sides is 16 units long, and we need to find this length, the length of the other side, the third side. So let's say this length is x. Now applying the Pythagoras theorem, we have 16 square plus x square is equal to 20 square, right? 16 square is 256 plus x square is 20 square is 400. To find x, we first need to solve for x square, and to solve for x square, we need to subtract 256 from both sides. And therefore we get x square is equal to 400 minus 256 is 144. And therefore x is the square root of 144, which is 12. So this side length is 12 units. Making sense? Great. Now we shall see how to make use of this knowledge on the Pythagoras theorem and some basic knowledge on triangles that I think we all have to find out the sine, cosine and tangent of some very important and common angles you would come across: 30 degrees, 45 degrees and 60 degrees. The 45-45-90 triangle is one that's got two 45 degrees and one 90 degrees in it. So it's a right angle triangle. And here's a 45-45-90 degrees triangle for you. Let's name the vertices as A, B and C. Now these two angles being congruent, you know this triangle is not only a right angle triangle, it's also an isosceles triangle, and these two side lengths AB and BC are the same. That's the property of an isosceles triangle, right? I hope you know that. Let's assume that this length AB is 1 unit long, and therefore BC will also be 1 unit long. Now we can easily find the length of AC using the Pythagoras theorem. And this is how. We could say that 1 square plus 1 square is equal to AC square, because AC is the hypotenuse in the triangle. Now 1 square plus 1 square is 2. So we have AC square is equal to 2 units, which means AC is equal to square root of 2 units. So we have the three lengths in this particular triangle. If it's a 1 over here and a 1 over here, it has to be a square root of 2 over here. Now, let's try and find out the three trigonometric ratios, sine, cosine and tangent of, let's say, angle C. Sine C, which is the same as sine 45 degrees, because C measures 45 degrees, is equal to the opposite over the hypotenuse. So that's 1 over square root of 2. Similarly, cosine C is the cosine of 45 degrees, which again happens to be adjacent over the hypotenuse, and that's equal to 1 over square root of 2. And tan C is equal to tan 45 degrees, which is the opposite over the adjacent, which is 1 over 1, which is 1. So we have our values. Sine 45 degrees and cosine 45 degrees are equal to 1 over square root of 2, and tan 45 degrees is equal to 1. Our next job is to find the sine, cosine and tangent of 30 degrees and 60 degrees. And to do that, we start with an equilateral triangle. Let's name the vertices as A, B and C. And just as you know, all three angles in an equilateral triangle are congruent, have the same measure, are 60 degrees apiece. 180 in all, divided by 3 is 60. And the three sides are also the same length, right? So let's assume, you could assume any side length. I'm going to start with a 2. So I'm going to say each one is a 2. 2 units long. And the next thing I do is I draw an altitude from A on the opposite side, which is BC. Now what's an altitude? An altitude is a line that meets the other side at 90 degrees. So we have a 90 degrees or a right angle over here. Let's name this point as D. Now if you look at the two triangles ABD and ACD, are they congruent? Yes, they are. You could go on to prove that they're congruent, but the easiest way to convince yourself is to say that this is perfectly symmetrical. You know, an equilateral triangle is very symmetrical. So when you draw an altitude, it should split the triangle into two equal parts. And therefore, this angle out here is a 30 degrees, which of course is the same as this angle. The two add up to 60, right? Now we are going to focus our attention on one of these two triangles. Let's say the one on the right. Notice that now we are looking at a right angle triangle, which means we can apply the Pythagorean theorem. This one, DC, must be 1, exactly half of what BC is. And we already assumed AC to be equal to 2 units long. So is there a way we could find out the length of AD? Yes, we could, using the Pythagoras theorem on this triangle. The hypotenuse is AC, which is 2. So we could say that AD square, that is this length, square of that, plus DC square must be equal to AC square, or AD square plus 1 square is equal to 2 square. Now 1 square is 1 and 2 square is 4. So AD square plus 1 is equal to 4, therefore AD square must be equal to 4 minus 1, which is 3, and therefore AD is the square root of 3. So we have our number. Provided this length is 2, it doesn't matter whether it's 2 or 20, because we aren't here to find out the actual lengths. We are here to find out the ratios of the lengths, and as long as the angles remain the same, 30 and 60, the ratios will be the same. So to find out sine 30 or sine 30 degrees, we could look at this angle and say that it's going to be the opposite over the hypotenuse, which is 1 over 2 or 1/2. Similarly, cosine 30 degrees is going to be the adjacent, that's square root of 3, over the hypotenuse, which is 2. And tan 30 degrees, you got it right, it's the opposite, 1 over the adjacent, that's square root of 3. Now if you want to find out cosine 60 degrees, you could either use this angle, sine 60 degrees and tan 60 degrees. Yeah. Or if you remember what we learned towards the beginning of this lesson, now cosine 60 will be the same as sine 30, right? Cosine theta is the same as sine 90 minus theta. Similarly, sine 60 is the same as cosine 30. And tan 60, you know what to do, just flip it over. So you have square root of 3 over 1, which is nothing but the square root of 3. So that's all for now, folks. I hope you enjoyed the video. Hopefully I'll see you soon.